Shanghai Jiao Tong University. His research focus is on the networked cyber-physical system. His work draws upon theories and methods from machine learning, wireless networking, computer vision, and robotics to build robust and cooperative intelligence in edge autonomous system. He is a recipient of MLSys Outstanding Paper Award, ACM Mobisys Best Paper Runner-Up Award, and COMP AP ICM Outstanding Winner Award. Dr. Hang, thank you so much for being with us this morning for this series. The floor is yours. Thank you.
Thank you. Thank you so much, Prakash. Thank you for the warm introduction, and thank you for inviting me. Hello, everyone. Glad to be here. Let me reshare my screen again. Is my slides available?
Yes, good.
Cool. So, yeah, so pretty much that's my background. I worked 1.5 years in Waymo before joining UC Riverside. In Waymo, I was working on perception and mapping. Today my talk is about towards networked cooperative autonomy. So let's get started. So over the last few years, we've already seen some autonomous systems deployed in our daily life, right? Like the Tesla vehicle, the drones, the last mile delivery vehicle, and even some Land Rover robots in shopping malls. So here are some statistics, right? So for Tesla, I think everybody has been aware of their progress, right? Since as of 2021, they have already accumulated over 2 billion autopilot miles. And in 2023, over 120 million full self-driving miles. And recently, they released the Autopilot version 12, which is the first end-to-end trainable model, which is widely praised on social media, being revolutionary, a new version of Autopilot. On the other side, Waymo has also been targeting level 4 self-driving robotaxi. So their journey has been quite long, ever since 2009, I think. So as of 2020, they have been offering over 4,000 trips per month. And 2023, that number becomes 60,000 rides per month. I think now it's already 150,000. So they're being exponentially scaling, as you can see, from 2020, 2023, and 2024. They started from Phoenix, Arizona, and then expanding to San Francisco, Los Angeles, Texas, Austin. So they got a CPUC permit, which stands for California Public Utility Commission, which is the commission to issue the permit to companies who wants to charge for ride sharing. So that means they are actually offering ride sharing for charge as a charged service, as a paid service. So the way towards today was not very smooth, right? We had a few accidents, actually fatal accidents, back in 2016, 2018. So 2 incidents from Tesla, 1 from Uber. The bottom left one is that the car cannot recognize the concrete barrier in the middle of the highway. And the bottom right one was the car cannot recognize a pedestrian crossing the road. If you think those are pretty ancient history, just last year, right, September 19th, 2023, this is what happened in UT Austin campus. So a bunch of cruise vehicles are stuck in the 3-way intersection. I'll play a video here. So this is around it. So that's the reason this traffic jam is causing trouble. So before I talk about how my research can actually help improving the self-driving cars, let's revisit the classic self-driving stack. So conceptually, we are we can divide the stack by 3 stages: perception, localization, planning. Perception, well, the car is using advanced 3D sensors like LiDAR, stereo camera, radar to sense the environment, right? So here's a result, point cloud from the LiDAR and the images from a pair of stereo camera. Because of the availability of large amount of data, now we have pretty good model to do perception, do this object detection in both sensor streams. For localization, the idea is to register those landmarks like this left turning sign, traffic light, into a map. And so that when you see the map, when you see those landmarks again, you can precisely localize the car's position. Here is not only the GPS position, but also the yaw pitch roll, so 6 degree of freedom pose. Here is an example of the map. This is a fully reconstructed dense point cloud map. This is from Nokia here. You can see this kind of map can capture the precise geometry of the building, the road, and the cars parked on the roadside. So in terms of planning, the idea is to detect those objects, traffic participants, track those objects, find the drivable space, and those are pretty much standard computer vision tasks like detection, tracking, segmentation. And using those task results, you can create a 3D model around the car and then find a viable path to the destination. So here's an example of Zoox. So this is a pretty typical classic scenario, nudging around double parking sedan. So if you look closely, I can play the video again. See if I can, yeah. So there's a red fence appearing, disappearing, right? That fence means the car is basically determining whether the path is executable or not. Because there is a other car, a black vehicle on the opposite direction, which could be moving forward, which means the path planned is not viable, spatially or temporally. But then the car realized that the black sedan is also parking. So then the car decided to move forward and the red fence has disappeared. So in the next few slides, I'll talk about how these modules can be unreliable. So for perception, let's see, we're a driver on this black car. We're driving on a single lane highway. There is a blue car driving in the opposite direction. So if there is a car in front of us that could block our vision, so this would be what we see. So in this case, similar to the sedan, double parking sedan nudging scenario, right? If we were to overtake this red car, we need to risk changing lanes to the left and occupy the opposite direction lanes. And there is a risk of colliding with the car in the opposite direction. In terms of localization, let's see we register the features into a map. And then when we use the map to localize, it could happen that it's a street cleaning day, right? All the dynamic cars are gone. You can still see some features that's being registered in the map, but also those parking cars are gone. And there could be also new obstructions, including that previously registered feature. There could be also removed occlusion that reveals new features that was previously invisible. Right, so all those 3 kinds of mismatches will cause instability in localization. And when it comes to planning, this is towards the end of the stack. So every error in the earlier module will be compounded and affect the planning. Right. So for example, here in this case, the detection missed the black van. So if we were to create a 3D model using the detection results, we would have a wrong model. And so the planner could have planned a path crashing into this black van. In the next 3 slides, I'm showing 3 scenarios. The overtaking scenario we've already mentioned, right? This is done in the color simulator. The left side is the point cloud, the right side is the bird eye view, and the bottom is the front view camera. So I've already talked about the risk here. Another similar scenario where the black vehicle is trying to turn left, but there's also a yellow truck trying to turn left in the opposite direction. So you can see that red sedan is completely occluded. We cannot see anything around it. And in this case, there is a risk of colliding. Right? By the time we see it appearing behind the orange truck, it could be too late. The third scenario, we call it red light violation. So the car can be going straight through the intersection, but there could be a red car rushing a yellow light, right? And because of the occlusion on the left side, a line of cars trying to turn left, waiting to turn left, we have no information behind those yellow trucks. So again, there's a risk of colliding to the red light violator. So to summarize, the cause of the unreliability for perception is the occlusion. For localization is the outdated maps, the changes in the environment that doesn't match the map. And for planning is the imperfect machine vision across the stack that could cause the planning to determine a risky route. So in this talk, I will talk about a few works to address those unreliability. For perception, I'm proposing cooperative perception. The idea is to use peer vehicles around you and share what they can see to your perspective. So essentially augmenting your perspective to invisible area and beyond sensing range. For mapping, I'm proposing a work called COMAP that leveraged also peer vehicles observation of the map change and do the detection and update the map in real time so that every vehicle can have up-to-date map constantly while cruising the street. And finally, for reliability of machine learning model deployed on edge in general, I will talk about a work called MX-ray, which provide the visibility into the execution and deployment process of those models onto edge devices. So through this line of work, I guess the general trend or research agenda is to build cooperative, real-time, verifiable autonomy. Let's get started with perception. So the idea is to share what the front car can see to the rear car, the follower, so that we can augment the view, right? So this paper published in Mobisys 18 is called AVR, Augmented Vehicular Reality. So it's very simple, just to share what the red car can see wirelessly through V2V connection, V2V wireless communication, and put the blue car in the receiver's perspective. However, so the end goal is to achieve augmented view like this, so we can see through the car and see understand what's invisible. So a little bit related to work and background. So I think a lot of people will be working on autonomous cars, and majority of them working on single vehicle perception. So again, the limitation here is line of sight visibility. We have a lot of models, we have a lot of data sets, but mostly are focusing on one single vehicle traversing through the city or the highway. So it's not clear what can be done beyond line of sight visibility as of 2018. And but a lot of work from the networking community, mobile computing community, has talked about connected vehicles. It's not a new thing. The vehicles are connected to the cloud. However, the message that's being transmitted is basic message, namely where their position is and what the car's velocity is. There's no sensor data or sensor perception results being shared through V2V connection or V2X connection. So cooperative perception is the idea of sharing what other vehicle can see and what you can see to each other, right, to help each other to build extended 3D vision. Here are some examples. The idea is being applied to both stereo camera reconstructed point cloud and LiDAR constructed point cloud. this is the exactly same scenario, a leader car and a follower car. The leader point cloud is shown on the top left of each set of pictures. The followers on the bottom left, and this one is the merged one, right? So in the case of stereo camera, the range was really limited. So if you can merge the other car's view, the range is doubled basically. In the case of LiDAR, the range is not a problem, but the visibility is occluded by the leader, so the follower cannot see it. But by sharing the leader's view, you can now see it. To do this, we have to address several challenges, right? So first of all, we need a very accurate positioning. Here, we don't mean the positioning of the car itself, but a relative position between transmitter and receiver. So let's see the transmitter detect the car at the position D in the transmitter's perspective. And we need the relative position between red car and black car. So we can calculate X, which is the blue car's position in the receiver's perspective, so that we can put the point cloud or camera data being shared to the right position. And also the bandwidth between V2V is very limited. So transmitting the whole point cloud or densely reconstructed object is very challenging. Also, cars can be driving at 80 miles per hour, so everything can happen very fast. We need very low latency. Otherwise, the information being shared is going to be stale. It's going to be not useful. So we have several contributions to address these three challenges, like using 3D feature map to do relative positioning, do dynamic object extraction to reduce the bandwidth, and do motion prediction to hide the latency. So I'll skip over some of the details, but show you some video demos. So here's the experiment setup, right? We mounted a stereo camera on top of the car and connect that to a laptop, and then laptop also connected to an access point, and the two cars have a similar setup. We're using the bridging mode between the two access points to construct the wireless link. Right, here's the photo of the experiment. This was done on USC campus, so actually this is my car and my lab mate's car. So the idea of the experiment is to show that we can actually do this by merging a leader's view to the follower. So here's the video demo. We did this on the top of a parking structure. And those green dots are the features to detect and register into the map. And those features correspond to the red dots in this map, top left. And once we have the map, we can localize. And here she's showing the leader's view and the follower's view when we're driving together. So when the leader transmits objects to the follower, they can be merged to the follower's extended view. You can see now that extended view, previously invisible objects are now visible because of the sharing. Right? So ever since then, this area has really been taking off. The idea of cooperative perception can help make better driving decision is really widely accepted. Right? So in the computer vision community, there was a paper called V2VNet from Uber, back when Uber was still in the business of autonomous driving. So the idea is to encode the point cloud into some intermediate representation and share the representation instead of the point cloud, and use the convolution neural net to fuse the shared information and do the detection. And by the time of 2022, transformers has come out, right? So people think about how to use transformers to better attend to different kind of encoding. So this paper called V2X VIT, region transformer, use transformers to merge, to do the fusion and do the detection. And the idea also expanded to different tasks beyond detection, right? So this paper, COBE VT from Coral 22, is doing map segmentation. So basically using other vehicles information to augment the map segmentation based on onboard sensors. In the communication community, there was also different kind of work talking about how to manage this sharing between vehicles. So F-Cooper is a late fusion algorithm. So instead of sharing point cloud, we can share bounding boxes. And ENP discussed how to better schedule those transmissions. So they divided the space into Voronoi triangles. So each car is only responsible of sharing the data within the triangle nearby, so that based on the coordinated scheduling, the whole space can be covered by a few transmitter cars. So beyond perception, we can then talk about how can we apply cooperation to other modules in the stack, right? So in the industry, there is a trend just the last 2 years of converting traditional modular design like this perception localization planning into an end-to-end module. As I mentioned, Tesla released the version 12, which is the end-to-end trainable module, right? So the idea is to combine some modules and use one or a cascade of neural nets to take the input directly and output the final decision, final control or prediction task decision. So, for example, this paper called 1D LiDAR, which is a paper I've done during the time in Waymo. Basically, this paper expanded the data set of Waymo open motion data set to include LiDAR raw data, so that instead of using the bounding box detected by detection modules to predict the motion, now you can use the raw sensor data and do this perception, detection, and prediction together, end to end, right? And this end-to-end idea doesn't stop at prediction. It can go all the way to planning. So from perception input to planning directly. So there's this work called Coopernaut, which is published in CVPR 2022, is a work done when I was in Stanford in collaboration with UT Austin. So the idea is, how do we leverage this shared information to actually do better control decisions? So we took the red light violation scenario and trying to understand how those information shared by those blue circle, any of the 3 blue circle vehicle can help we make decision. So the setup is similar. We have cars, we can encode the LiDAR camera data and then into representations, and then we can create a graph of the vehicles around each other. And we can train an ego vehicle policy when it's aware of other vehicles' representation or fusing other vehicles' representation. Or we can also train a multi-agent policy when all the agents are aware of each other's representation. So here's an overview of the model architecture. So we use point transformer to encode the LiDAR points, and we use a really lightweight representation, just 128 element. Each element is 128 number or descriptor, plus 3 XYZ coordinates. So the benefit of a point transformer is that you can encode the feature, but still preserve the XYZ, the physical location of the feature. So that when you share the physical feature, you can use the XYZ to transform from the transmitter's perspective to receiver's perspective, given that you know the transmitter receiver's position using a common map. So then after transformation, we can then do a voxel pooling and to reduce the size even further before merging with the ego vehicles encoding. After merging the ego vehicles encoding, we can use another point transformer to aggregate the information and output control decision directly. So to train this model, we use the behavior cloning and Dagger process. So behavior cloning is basically applying the expert policy to the scenario, gather what the other expert should do, and clone that behavior to train the model to do exactly the same thing as the expert is doing. A Dagger process is to increase the robustness of the trained model. So you use the pre-trained model, the cloned model, to explore the scenario even more. So the trained model would not behave exactly the same as the expert policy. The small deviation, the numerical differences, let's say steering 90 degree versus 89 degree, those small differences will cause the car to deviate from expert policy trajectory and explore new scenarios or new conditions. And during those new exploration, we then apply the expert policy again, right? So that we can gather what should be done in these new scenarios and train again to further improve the robustness of this model. Here's the expert policy, right? We designed the expert policy using a very simple A-star planning algorithm. And given that the car knows all the ground truth, all the environment, global knowledge, right? In the left, there's limited knowledge on a single vehicle. On the right, we have unlimited sharing, assuming no bandwidth limit. The car has global knowledge, and what would the A-star planner do? So in this case, it can predict the collider's trajectory. The green is the near horizon, temporal horizon. The blue is farther in temporal, 10 seconds into future horizon. So by predicting what's the trajectory of the collider, then the A-star planner can actually stop and wait for the car to cross and then move forward. We still took the 3 scenarios: the overtaking, left turn, and red light violation. And we used the expert policy to predict all the objects around and use the spatial temporal collision detector to basically modify the A-star planner. A-star planner just plan the path. But if the path is colliding with other path, either spatially or temporally, or actually say spatially and temporally, and then the A-star planner will not be executed. It will just stop and wait until the other car pass by. So here are some training results, right? So it's still the same scenario, overtake. Without sharing, the car would make a lane change, and Cooper choose to wait, and then after the car pass, it will take over the truck, overtake the truck, sorry. So this is the left turn scenario. You can see the bottom is the point cloud, right? So in the no sharing case, the car is still occluded. In the sharing case, the red dots are the shared representations. I have trouble pulling this video. So the car can see it, and Cooper decide to wait for it, and then and move forward. In the third scenario, similar, because of the sharing, the Cooper agent decides to wait. The interesting here is the expert policy. If you remember from previous slides, the expert policy actually waited right in front of the crosswalk. But Cooper here decide to stop very early, like 2 truck distance before the crosswalk, and to avoid the collision. We did some numerical analysis, right? So we're comparing Cooper to no sharing, early fusion, or a simple voxel graph neural net, which is what's been done by V2VNet. We achieved a better result, successful rate, SR, success weighted by completion time, SCT, and the collision rate, CR. So in all three metrics, I think Kubernetes is performing pretty well. In the meantime, we actually require very little bandwidth. The early fusion requires 60 Mbps to transmit raw data. The VTVNet require 5.6, and we only need 5.1 megabits per second. And you may ask, so now you've shown this can be done in one or two or three cars. How can we share? How can we expand this capability to all the vehicles in a crowded scenario, right? So in this case, you could have a very busy intersection. H is trying to turn left. A is going straight. C can share A's position, right, to tell H when to make the turn. This is the exact same left turn scenario. And symmetrically, C is turning left, I is turning right. H can tell C I's position to inform C when to make the turn. So the point is there could be many such communication happening in a crowded scenario. So how can we expand this capability to give the augmented vision to vehicles in need, right? There are quite a few challenges to do that, right? To begin with, how do we figure out which object is of interest to whom? How do we orchestrate this, coordinate this communication? There must be some beacon mechanism to let everybody know who they are, where they are, what kind of information they're interested in. And finally, assuming that we know all those information, how do we schedule this transmission optimally? So because the bandwidth is very limited, they share the same wireless channel. So to solve that, we propose AutoCost. It's a paper published in Mobisys 2022. It's a scalable infrastructureless cooperative perception for distributed collaborative driving. The idea is to enable basically everybody to see, right? So here, vehicle A can see all the red dots. Vehicle C also can see, every vehicle can see what they need to see. So I'll skip the summary of contribution and go to the meat directly. So we basically decouple the pipeline, right? So each vehicle, in order to do this sharing, each vehicle has to do some spatial reasoning, exchange metadata through the control channel to other vehicles. And there should be a scheduler, ideally distributed, to compute when to share information. And based on that schedule, you can then exchange sensor data to the data channel, separately from the control channel to other vehicles. Finally, merging the sensor exchanged, you can do trajectory planning. Right. So we decouple this to two planes, the control plane and data plane. The control plane handles the metadata exchange, including pose, trajectory, objects, and occluded area. And there's also the distributed scheduler. In the data plane, we analyze the occlusion relationships, right? Which area is occluded for each vehicle locally, and also analyze the relevance, right? Whether the occluded area is relevant to me based on my trajectory. If I'm going forward, even if something occluded in the backside may not be relevant to me, right? Also, the data plane handles the trajectory planning and data fusion. So here's a simple illustration of how to do this spatial reasoning. So we voxelize the point cloud into grids, right? And each grid, we categorize them into three types: empty, ground, and object. So this part, if you can see my cursor, the yellow one is an object, and this one is also an object. And for those grids beyond the object that's empty, we can pretty confidently say those are occluded grids, right? Invisible grids behind the objects. So we analyze those spatially and record and share those information as very, very lightweight metadata to others. So here's what we include in the control message or beacon. We include each ego vehicle's planned trajectory, detected objects, and so that the receiver can actually figure out the invisible area based on the detected objects, and then judge the relevance based on the trajectory. So the invisible area and relevance are implicit in the beacon message to make it more lightweight. And then we formulate this into optimization problem, right? So Xijk indicate vehicle I sharing object J in representation K. The representation means you can do bounding box, you can do intermediate encoder representation. You can also do raw data depending on the bandwidth availability. And the WPJ indicate vehicle P's interest in object J. So if, let's say, C is trying to send A's information to H, right? So WHA would be 1 because H would be interested in where A's position is. So then we can formulate the optimization problem into maximizing the reward function of the total interest of a particular object. And the object can be transmitted just in one representation, and the total schedule time for transmitting each object together should be less than the total time for this scheduling period. So this problem is pretty standard. There are NP, this is NP hard, but there are standard dynamic programming solution called MLSys. So we simulated when there are 40 vehicles, how long can we make the optimal decision? It's too long, right? 2.95 seconds per decision is too long. We need this to happen very fast, like maybe a few milliseconds. So because the cars are sending information constantly. So we designed a heuristic to rank all the objects by the reward divided by the time to share it. So the less time needed to share, the more interest, the more reward by the object will share by sharing the object, then the better, right? The higher priority. So we compared this heuristic with optimal performance. So we see the total reward is almost the same until maybe 8 or 10 future slots scheduled. And it's way above the agnostic, which is random sharing. So some end-to-end results, right? Based on this scheduling optimization, we were able to prioritize those objects that's really high priority of high interest to other vehicles. So the red one is autocast. The purple one is unlimited, right? Autocast use 7.2 Mbps bandwidth max. Unlimited means you don't have any limit on the bandwidth. You can see the performance very close to each other. Safe passage, right? Almost 100%. Zero crash, zero deadlock, a few near miss. Near miss means the cars are coming close by to like less than 2 meters from each other. We also compare that to EMP and agnostic. EMP is the Voronoi segmentation sharing method I mentioned before. It's a centralized way of sharing. So there is an edge tower, edge assistant to make the schedule. And because of the sharings through the edge, you have larger bandwidth. We resume a 50 Mbps bandwidth. But even that, you don't have good coverage, right? The safe passage is 60%, similar to agnostic random sharing, actually. We also evaluate how scalable is this. We simulated 5 to 40 vehicles. You can see the safe passage is exactly the same with unlimited until at 40 vehicles, it drops a little bit to maybe around 85% safe passage. We also use the real DSRC video to validate the scheduled transmission. We can see that the scheduled in blue, DSRC in orange. this transmission can basically keep up with what's being scheduled. And at the time, we still used the SRC, but now we're transitioned into V2X, CV2X. I see there's a question, but I'll maybe answer that later. Yeah, I'm kind of running out of time. Sorry. So this is a demo of AutoCast, right? When you have a lot of vehicles around, that occluded red collider can still be prioritized, so the car can make the right decision. So to summarize, for perception, we enabled extended vision beyond occlusion sensing range, and we coordinate and schedule this transmission at scale. So I'll move on to maps and a little bit HTML. I want to get to the robust HTML part too. So maybe I'll speed up a little bit. So nowadays, every company is collecting a map, right? Tesla, Waymo, Lyft, Apple. They use a fleet of vehicle to collect the map. There's a company called DeepMap. It's a startup company. They offer $5,000 per kilometer mapping cost. They are now acquired by NVIDIA. But you know, this expensive map is still vulnerable to map changes. As I explained before, if there are any things changing, it will affect the localization stability. So the idea of COMAP is to use a cross-sourcing approach to leverage all the vehicles to detect the changes and update the map. So traditionally, people have been focusing on odometry and mapping. They just want to use the sensors to figure out how much the agent move, which is what odometry means. But they care less about the mapping size, right? So usually traditional SLAM algorithm produce a very large map, which is inconvenient to share. So in the localization community, we use GPS, we use differential GPS, we use RTK, a bunch of optimizations, but they're still vulnerable to urban canyons, high skyscrapers to block the satellite. And their granularity is just not good enough for corporate perception. So COMAP is trying to do up-to-date map with robust fine-grained localization using very lightweight updated map. So I'll skip the primer on how SLAM work and maybe show you some of the results directly. So basically, we did a bunch of optimization. We detect the features. We use semantic segmentation to figure out whether the feature belongs to a dynamic object or static objects. And we only register those static objects into the map. And then we apply the XYZ coordinates of the feature to understand the location of the feature to improve the matching performance. So previously, we only used visual descriptor to match the feature. Now we match the feature with both a visual descriptor and geometry XYZ. So the video shows that we can actually keep up with the local mapping. So on the top left is the local mapping. You can see every frame is mapped directly. On the bottom left is the cloud. So we're transmitting segment by segment, and the transmission is very lightweight, 1 Mbps. So the cloud can keep up easily. This is the profile of latency, 350 milliseconds to detect changes and upload, 50 milliseconds to integrate, and 200 milliseconds to download. So less than 1 second, you can complete detection to distribution. Because of the lightweight update and the geometry addition into feature matching, we were able to achieve actually more robust matching, more robust localization with much smaller map size. So this configuration we talked a bit before, right? We mapped the environment during a busy day and localized in a street cleaning day. So because of the drastic change in the view, existing SLAM algorithm cannot localize. Right? OpsLAM2, Quick Sketch cannot localize. But COMAP can localize because we register only static feature, and we also register their geometry. And the map size is much smaller, 3.94 megabyte compared to 108 megabyte. Another interesting experiment. So we register the map when the car is driving through lane A, and localize the car when the car is driving in a different lane. And we want to see if the change of the perspective in a different lane can cause instability of localization. Right? It turns out that's true. OpsLAM2 can localize in the second lane, but cannot localize in the third lane, fourth lane, because the perspective changed too much. And because we added the geometry, we were able to localize even in the third lane or fourth lane. So to summarize, we enabled a live 3D map difference updates in less than 1 second, and robust localization using 30x smaller map with sparse features. Okay, and finally, I'm gonna go to the robust HTML part, which is a work I really like. So as I mentioned before, the errors in the previous modules can cause the wrong 3D model, right? So how do we actually ensure the model deployed on edge device is actually behaving as we wanted? So this work is called MLXray. It's a work done when I was in Stanford in collaboration with Google. It is published in MLSys 2022. We also win the Outstanding Paper Award in that conference. So the idea is to provide some visibility into ML deployment on the edge, because everybody knows ML models is like a black box. If there is any error, it's very hard to debug, very hard to get any insight of what's going wrong, right? So you may think that the lack of performance, the detection missing, is a data problem. If you have better data, maybe the model can be better trained to perform better. But the point I'm on the stress here is there's no debugging capability. So the model can never be 100%. So whenever there is an error, how can we debug this, right? In the profiling benchmark community, they very much stress on end-to-end analysis. What's the profile? What's the latency? What's the performance? But still, the model is a black box. They treat model as a black box without analyzing what's happening in the model. So what MLXray is proposing is a verifiable edge ML. We use per layer validation to enable debugging and monitoring on the edge. So so take a step back. What do you need to deploy a model in general, right? So let's say we want to deploy an image classifier on the mobile phone, right? So you have somebody train the model for you. You can download them on the cloud. You have a cloud model, and then you have your phone. You have an image from the camera. You have to design some pre-processing functions like channel extraction. The Android phone comes with YOV format. You need to convert it to RGB format. You also need to resize it to a smaller image that the model can take. And you also need to convert the numbers from 0 to 255 to 0 to 1 floating point, integer to floating point. And some models assume 0 to 1, some models assume -1 to 1. So you have to convert to the right format. And also you have to rotate the orientation because a lot of models are trained in the landscape image, but the phones usually take vertical portrait images. And for the cloud model to optimize for limited resource on the edge device, normally people would do constant folding like batch norm, combining the batch norm layer with the convolution layer so that we can access the GPU less frequently. Combining the ReLU layer with the convolution layer, right? So we also do quantization to make it smaller footprint when executing on the edge. So then we have our edge model, and we can input the image to get results. So what could possibly go wrong in this process? There are many things actually. There is a disconnect between model developers and app developers. app developers doesn't know what's the assumption of the model. So if the model developer choose to get input in -1 to 1, that information is lost during the handover of the model. The web developer has no idea what's the model's input assumption. So it can only guess, right? If you guess wrong, the image will be weird and the performance will drop. There could be also quantization issues, right? The model can have arbitrary range of the numerical values. And if there is a few outliers, let's say the majority of the data concentrated on the range, but there are a few outliers, but to quantify those values, you have to use fix the range 0 to 258 to quantize them. And you lose a lot of resolution because of those two outliers. There could be also kernel optimization issues, right? Some kernel is optimized for specific hardware, but if you use that kernel to a different hardware, it will cause a very long latency. So how do we debug this? All right, there's really low awareness of these issues. There's little visibility into the edge black box. There's a tedious reverse engineering. This is what industry is doing, which is basically logging every layer's output and compare to a reference pipeline. So what we're doing is to provide an automated toolbox for people to do that validation really quickly, right? So the idea is we log those layers output by just a few lines of instrumentation code. The red dots are the preprocessing layers output. The green dots are the model per layer output. And the blue dots here is a layer output for a reference pipeline. So the framework MXRay just compared that layer output directly and produced a debugging report for you, right? So it has both end-to-end performance accuracy result, but it also has a per layer RMSE, root mean square error comparison. And it can also tell you if you are suspicious on some specific processing function, like channel extraction, rotation, right? You can write a small user assertion function, and the framework can tell you if the assertion failed or not to confirm your suspicious reason. Yeah. So a reference pipeline could just be the cloud pipeline, but it can also be others to focus on specific component to compare. Right? For example, if the basic comparison is the optimization, right? You can compare the cloud pipeline versus a optimized pipeline and see if they're the same. You can also compare unquantized versus quantized, or you can compare reference operators versus optimized operators. So those breakout can really focus the debugging process to a specific component and validate that component is functioning correctly. So I'm going to show you a few interesting results in the last few minutes. So here on the x-axis, there is a bunch of models, MobileNet, Inception. On the y-axis, the accuracy. So the blue bar is the reference baseline, right? The orange is the mobile pipeline with floating point. The green one is the mobile pipeline with quantized integer weights. The red one is optimized kernel for Android using the quantization. So you can see there's some missing bars here, right? For example, MobileNet version 2 doesn't have a red bar. That's because the quantized optimized kernel actually has a bug. So we actually look into each layer's RMSE. Since the second layer, so the orange one is the reference pipeline, reference kernel versus the baseline. The blue one is the optimized kernel versus the baseline. So if everything is correct, it should perform exactly as the orange line. The error should be really small, meaning the numerical computation happening each layer should be the same as the baseline. But the quantized optimized kernel has a bug in the second layer, which is the depth-wise convolution layer. Ever since that layer, everything else computed is different, is already wrong, right? So this can immediately figure out where the bug is and how to correct that. Also, this figure shows the preprocessing can also have a huge impact on accuracy. So these are things that really nuanced that people don't care about, but it actually matters. For example, resizing. Resizing, what can happen with resizing? You can use area averaging function to resize, right? For example, 50-50 pixel to 5-5, you can average them. But you can also use triangle interpolation to resize them. So those two different methods to interpolation versus averaging can cause different pixel values in the resized image. And that different pixel values will cause a different accuracy number. So you can compare the orange with the blue, right? Every orange bar is different from the blue. It's a little higher or lower for different network. This is maybe a little bit minor issue, but if you look at other issues like normalization, right? If your normalization is normalizing to 0 to 1 or -1 to 1, that can cause a huge difference, right? It can drop the performance up to 20% in some case, the blue bar versus red bar. And this is common across different tasks. Classification, detection, speech recognition, they all have some kind of resizing, channel extraction, normalization, those pre-processing functions, which can cause accuracy degradation. So to summarize this paper, tap into the ML execution to understand when the model fails and why, enable verifiable ML and continuous ML monitoring on the edge. So that concludes my talk. So I've talked about cooperative autonomy and a system for edge ML. So I'm open to questions.
Thank you, Dr. Hang, for the fantastic presentation. I appreciate for sharing your insights. So we are going to go with your questions here. Let's see. Okay. Thank you, Dr. Chow. For CoperNet's point transformer, I believe we'll need a significant amount of data to train MLP encoding function. Could you have any insight on how large your training?
Right. So we collect the data in the simulator. We apply fuzzing to all the parameters, like how much is the speed of the collider and when does the collider start to drive, right? So I think we have about 50 to 60 um, uh, traversal of the same scenario, and that was our data. The data set is actually available on the website for training.
In your discussions or training with these uncertain scenarios, like vehicle malfunctions or poor network conditions, or maybe the all of a sudden maneuvers between left and right turns, or conflicting data from multiple sources of data between vehicle sharing, I was wondering, have you considered these uncertain scenarios conditions in your training?
Yeah, that's a good point. We didn't do a lot of uncertainty, I guess, especially in the Kubernetes, we didn't do because we want to focus on how to leverage that information from invisible area. But I guess that's a good point. If we can add random behaviors to the simulator, we can improve the robustness of the model.
You mentioned deadlock. Can you elaborate what are those deadlock situations that you are
Right.
defining in your paper? Yeah.
Right. So, for example, in the overtake scenario, right, the car change a lane, and then the opposite direction car also come. So the car is basically facing each other, and, and nobody wants to back off. So we call it a deadlock.
And okay, I'm just curious to see the transferability of the trained model between one vehicle type to a larger or medium scale vehicle types. Do you see, I'm, what is is it easy to transfer, or there are some issues in that certain factors that you need to consider when you transfer these models from one vehicle type to the vehicle?
Yeah. In this particular scenario, I don't see a problem, but I do acknowledge the difference, right? So in especially for trucking on highway, a lot of things designed for local urban driving is not applicable directly to highway driving for truck because the truck is heavy, it takes longer to brake, it needs a longer horizon to plan. In the city, you need maybe 50-meter enough, up to 100-meter enough. But on the highway, especially for trucks, heavyweight, you need the 300-meter, even 400-meter. So yeah.
Great. When you talk about cooperative perception and when we, is your edge devices are communicating to the ECUs within the vehicle, or how is that, how did you do this? I'm just curious because, yeah, I'm just curious as how one should look at, as futuristic to how do you make sure the ECUs are indeed, are listening to these edge devices or they're part of the ECUs?
Yeah, so the majority of the sensor we used is external to the ECU, like stereo camera, LiDAR. We've just mounted them on the car. But the communication module, the V2X radio, does have a CAN bus interface. So that one can take CAN bus message and also put message on the CAN bus. So I assume that would be the good interface to do that.
Sure. How do you see some cybersecurity vulnerabilities play into role when you talk about vehicle-to-vehicle communication? What type of security features that you are, are you assuming anything or?
Yeah, this is the interesting part. There's pretty much blank, I feel, in the V2X security. Um, I should take that back. I should say that there's a lot of things to do, a lot of room to contribute in V2X security. The assumption in this work is there's no attackers, right? There is no malicious sharer or cooperator. If there were, then we actually discussed this. We have another paper in submission about how to differentiate who is the malicious collaborator. And you can think about majority voting, authenticator, right? Those approaches. But I think in general, this space is pretty much open.
I may have missed, are you using edge devices? Are you using like NVIDIA's thing, or what are your edge devices that you
Um,
have?
Yeah, so for the real experiment, we're using the laptop. The laptop has a NVIDIA GPU. For the X-ray work, we use the CPU, but we also use the what's that? The Coral TPU thing. Yeah, so um,
Sure. Um, You touched about localization with single and multi-lane. Did you, in your simulation, did you consider crowded or, many vehicles, the density of the vehicles as they go? Can you shed some light on that to see how autonomy is going to be realized in those type of situations?
yeah. I talk about the AutoCAD work, right? Which is solving that problem. Um,
Yeah, I saw that optimization problem, but do you see
yeah.
any unboundedness or any infeasible conditions that you'll end up in when you increase the variable size or constraints in your model?
Yeah, so the model actually has to have a pre-allocation of how many vehicles are contributing to the sharing. Um, the transformer can attend to any number of tokens, right? But still, there is a maximum limit. I think that limit is still much bigger than what's available in the road.
Sure.
Yeah.
One other question. How about environmental scenarios, weather conditions, terrain, or all those scenarios? Have you considered that also in your training model?
Yeah, no, we didn't consider that. That's a good point. So I think everybody is moving towards multimodal fusion, right? I didn't talk too much about that in the work. Most of my work is single modality. I think to counter whether we have to leverage multimodality to provide more redundancy, right? Um,
I do like your verifiable edge concept. We're also developing an edge test bed for, are setting up in our lab, and it has collections of 10 AGX and nanos and some Raspberry Pi to do some attack vector modeling, deploying AI and machine learning workflow to detect certain threats. But what is your take on of students who are listening, who wants to, choosing a topic in this area on dissertation? What are those challenges that you would recommend for them to proceed, as a takeaway message?
I think this space is huge. It's a very multidisciplinary area. So if you're interested in computer vision, you can maybe look at multimodal perception, right? Handling weather conditions. If you're interested in communication, you can look at how V2X can actually help this cooperation to happen. There's still a huge gap between what's available in V2X and what we want to have to enable this collaboration, right? There is also the cellular part. So instead of V2V direct communication, you can do V2I. How can the infrastructure, 5G, 6G, NextG, help cooperation and vehicle to infrastructure collaboration, right? There are also sensors mounted on infrastructure. There is also huge space on security. How do you ensure the vehicle sharing information is secure? It's a multidisciplinary and a very huge space.
Well, thank you so much for your time this morning. I think we're going to conclude the talk with this, but I think you will receive a nice plaque from UND and our dean's nice letter. I think appreciated for taking the time. I think we should be in touch to see how we can work together, on
Yes,
going
look
ahead.
forward to that. Thank you.
Thank you so
For
much,
inviting me.
Dr. Hang. Take care.
All right. See you guys.
Bye.